We've introduced the idea of a binary tree and now a binary search tree, and we looked at the properties of the binary search tree and how to insert something into a binary search tree. In this video, I'd like to talk about how to remove something from a binary search tree. Now, the removal process isn't really different than the insertion process in the sense that it also leverages this idea of recursively traversing the tree, knowing whether to go left or right in order to remove an element based on examining the value of a node, the data at the current node you're at, and deciding whether to look down the right branch or the left branch in order to find the node that you want to delete. The additional complexity of removing a node comes from the fact that you have to repair the tree once you take something out. So first of all, we need to find the node, and that process of finding the node is pretty straightforward. It's recursive as well. So the first thing to imagine is the base case. And a base case would be when you are currently at a node and it has no children. If it is the case that you are at a node that has no children and the data in it is the data that you want to remove, then you just set the parent node's branch equal to null. So in the picture here, you can see that the node to be removed is on the far bottom right, meaning it's the highest value in the tree. And when we want to remove it, all we have to do is set the parent node's right branch equal to null. And that just effectively gets rid of the node. Well, what happens to that memory? Once we set the parent node equal to null, there's no references to the child node and the garbage collector comes and picks it up. Now in a second case, we have found the node that we want to delete and that node has one child. We have to do something slightly different. What we have to do is we have to modify the parent link in order to hold on to the children of the node that we want to get rid of. All right, so in this case, we see that the light red or the pink node is the node that we want to remove, but we don't want to remove all the children as well. We just want to remove the data associated with that node. And so we want to hold on to that one child that we've got, whether it's the left child or the right child, and we want to have the parent's right branch, in this case, attach itself to that particular node. Then that pink node will go away, but the child node will still remain. Two cases so far, the case where the node you want to remove has no children and the case where the node you want to remove has one child. Both relatively easy to conceptualize. A little bit more difficult is the case when the node that you want to remove has two children. In this case, we want to do something that holds on to the children of the node that we want to remove, but maintains the binary search tree property. And so in order to do that, what we know is we know that we have some node that we want to remove. Okay, so this is pretty high in the tree. And we know that there are left branches and right branches that we want to hold on to. And we need to decide what do we want to replace the node that we want to remove with. Well, we have two options. The first option is what's shown in this data set, which is that we want to find the lowest value of the right branch and move that into the node that we're removing. Because if we find the lowest node of the right branch, our binary search tree property will hold. The lowest node of the right branch will be higher than everything on the left branch. Since it's being taken from a child of this node, we know that the overall binary search tree property remains the same. So what we then do is we say, okay, recursively, let's remove the lowest element from the right branch. Well, now that node has one child as well. And so if we imagine recursively, well, let's just go through the process of removing that node. Then it repairs itself recursively. Now, the other option that we could have done that isn't shown in this diagram is instead of finding the lowest element of the right branch, we could have found the highest element of the left branch and replaced the node that we wanted to remove with that element. Both of those are options. It's a design decision that you can make when you're actually implementing the code. So three cases: no children, one children, and two children being conceptually a little bit more difficult. Let's dig into the code a little bit for this and see how it works. And let's talk about the efficiency of these operations. Now, the key aspect of a binary tree is that it relies on knowing a lot about what's down the left and right side, because as we build the tree, we maintain that property, and as we remove things from the tree, we maintain the property. So if any time we have a binary search tree and we just want to find whether or not there's an element in that tree, that's only going to take, and it's a balanced tree, meaning it has an equal number of elements on the left and right side, then finding that element is going to be order log n. That's because at every node, we get rid of half of the data that we have to look through. And so we end up, at most, having to look down the height of our tree, having to walk down from the root to one leaf, because at any moment we only have to go one direction. And we know that the height of a tree is log n, a tree that has n elements in it. That assumes that the tree is balanced. Now, an unbalanced binary tree looks just like a linked list, where we just, for example, if everything's down the left node, it could still be a binary search tree, but it's basically going to be an ordered linked list. And we know that the efficiency of finding an element in a linked list is order n. So you can see that as a binary tree goes from being balanced to being unbalanced, we lose the benefit of the divide and conquer strategy, and instead we start getting the efficiency of the linked list. This should suggest to you and motivate to you that it would be very helpful if there was a way that we could not only maintain our binary search tree property, but also keep our tree balanced. Because remember, having a balanced tree is different than having a binary search tree. You can have balanced and unbalanced, binary and unbinary. They're two different concepts. Now, if we want to add an element to a tree, the algorithm is the same, because as we walk down our tree and find where we want to add our element, we at most have to go down the height of a tree. All the way, when we add an element, we always go down the height of one branch. We start at the top, we go down to a leaf, and we add it at the appropriate leaf. And the worst that we're going to have to do is go down the height of the tree. And the height of the tree is log n when we have n elements in the tree. But again, if it's unbalanced, we're adding something to a linked list. And that may require us to go down the entire length of the chain. Finally, if we want to remove an element, again, the worst that we have to do is look down the height of one particular branch. Even though removing an element from the tree incurs a little bit of more work at each particular node, it still is only work that's done at one node in a path from the top to the bottom. So that's order log n. You can see here that the motivation for having a balanced binary tree for these data structures to be efficient is great. That's the motivation for the red-black tree that we'll look at in the last class. All right, let's take a look at some of this code, and thank you for your attention.